me just say a few words about Caleb. Uh, Caleb has done some really interesting work over the last few years. We started working together when he was a graduate student at Georgia Tech, did his master's with me, and transferred to MIT at the time that I was moving to MIT. He was willing to come a semester early. He played an absolutely indispensable role in helping to get our new laboratory set up here. He has done a lot of really interesting work on extremely high temperature liquid metal pumping and component and system development. And I think he's got some really interesting contributions that we should all hear about. So with that, I'll pass to Caleb and go ahead and present your dissertation defense.
All right, thanks, Dr. Henry. So the topic of this defense is thermal energy grid storage, which is a form of energy storage with the goal of enabling renewables. And this thesis focuses specifically on liquid containment and pumping. And so first of all, what is the problem I'm trying to address with this? So first of all, we know that fossil energy causes climate change. And so there's a push for renewable energy. But the main forms of renewable energy, including solar and wind, are intermittent, which means they're not available all the time. So with electricity, demand must equal supply because there's no fundamental storage mechanism. And so there's a few ways to do this with renewables where you can't control the supply. Four main ways. One is by improving transmission so that you could send the energy farther to a more diverse load or demand. Another is to have demand actually respond to availability. This is challenging at the consumer level, but potentially at the large scale, people could change how much they draw depending on the price of electricity. A third method is curtailment, which just means disconnecting the renewable supply when there's too much. So this is not ideal, but it's one way to at least prevent blackouts and maintain stability on the grid. And the last really ideal way is storage, which is just storing excess electricity and then dispatching it when there's a shortage. But because of the cost of storage, these other three techniques will probably be part of the final solution. But this thesis focuses on storage. And so with regard to storage, there's certain technologies that exist today, but they're either too expensive or geographically dependent. So lithium batteries can store energy, but they're too expensive to store energy for hours or days. And other methods like pumped hydro, where you pump water up a mountain, are limited to locations where there's lakes on top of mountains, essentially. And so what we're trying to do is implement a new technology that is both inexpensive and not geographically limited. And so the general approach is to use heat to store energy. The reason this is cheaper is because all materials store heat. They don't need to be processed. You just add heat and you can store it. And so that opens up the range of materials that can be used relative to chemical reactions like in batteries. But thermal storage is less efficient than existing forms of storage, usually something like 30 to 50% efficient compared to around 80% for mechanical or electrical storage. And so one way we can address this low efficiency is by trying to operate at high temperatures. And so if you look at the plot on the right, I'm showing around 550 degrees Celsius is the maximum existing liquid temperature used for heat transfer energy storage technologies today. And in this work, we're trying to push that out all the way to 2400 degrees Celsius. So this huge increase in temperature corresponds to an increase in the maximum possible efficiency defined by Carnot efficiency from 60 to 90%. And if the efficiency goes up, the overall cost of electricity can go down. So in this thesis, I'm going to go through the following topics. First, the general concept, then the cost of this idea compared to existing technologies, and then some of the main challenges to realizing this technology. So the first is just heating up to these extreme temperatures, converting electricity to heat. The second is containing a storage medium, which in this case is liquid silicon. The third is pumping. So we need to circulate the silicon between different components. And finally, some future options for the technology. So first, the general concept is shown here. If you look on the center left, we can have any electricity source as an input, and we convert that electricity to heat when there's excess. This is converted by pumping silicon past resistive heaters and storing it in a hot tank, nominally 2400 degrees Celsius. Then when electricity is needed, it's pumped out of the hot tank and into a heat engine, which converts heat to electricity. In this case, the concept is for the heat engine to use photovoltaic cells. Because the silicon is so hot, the pipes that contain it can directly radiate at PV cells, generating electricity. And a pump is critical to this technology because the silicon has to be moved from the hot tank to the heat engine and then back to the cold tank. And so the key questions I'm trying to address in this thesis are related to economics, heating, and just realizing the material compatibility issues with containment and pumping. So for economics, the main new thing here is that thermal storage, because it operates at lower efficiency, but can also be lower cost, there's a new regime of economics that we wanted to look into, which is what happens when you consider efficiency as a key variable in the trade-off. Generally, energy storage in the past has considered efficiency as a fixed variable around 80%, but there's different storage technologies that can range between 30, 50, 80% at different costs. And so I developed a framework to compare the effect of efficiency to the cost. The next topic is the effect of heating and how to heat above 2000 degrees Celsius affordably and with low heat loss. So while this has been done commercially, for example, in ovens for material processing, all of the existing technologies are very inefficient and involve active cooling of the heating elements to protect them. So we wanted to find a way to convert electricity to heat efficiently and affordably. And the third set of questions is related to materials compatibility issues. And so in this case, we're trying to contain liquid silicon in a graphite infrastructure. But these two materials react with each other. And so we wanted to know under what conditions can they be contained. And so some of the key variables are the porosity of graphite, which determines the cost of the graphite. So the key question was, is there an affordable grade of graphite that can contain silicon? The second question was whether there's an affordable grade of silicon that can be contained. And so the more impurities that are allowed in the silicon, the cheaper it is. So we investigated several grades of silicon. The third question involves whether the silicon carbide layer that forms when silicon and graphite react remains protective. So this layer can form a barrier preventing further reaction under certain conditions. And we wanted to know, does it remain protective under non-isothermal circulation? What this means is when I'm pumping silicon from the cold tank to the hot tank, so there's a temperature difference and the silicon's moving between it, does that cause a problem, or just thermal cycling by itself, just heating and cooling the heater system cause problems? And the last question is related to pumping and whether pumping or the act of a dynamic component causes the silicon carbide layer to delaminate, abrade, or cause the pump to bind and stop rotating. And so before I get into how we actually tried to make this happen, I just want to expand on some of the challenges with running these experiments. So like I mentioned, commercially, heat transfer with liquids has been limited to around 565 degrees Celsius. In the last few years, our group has exceeded that and reached up to 1400 degrees Celsius where we're pumping molten tin. And now we're trying to go up to 2400, which adds some new challenges. For example, we can't directly measure temperature. There's really no direct contact measurement system that can be used. So instead, we just have a hole cut in the insulation of the system and we measure the radiation with a pyrometer. And so it's very hard to observe the system because of this high temperature. Another challenge is that silicon expands when it freezes about 10%. So this is a massive expansion. Kind of similar to how water expands when it freezes into ice. What this means is that at the end of each of these experiments, the containment system actually breaks because of the stress that's developed. This isn't necessarily a problem for the full-scale system because the idea is to keep it liquid, but in the experiments, it means that each experiment is sacrificial and the system has to be rebuilt each time. And the last challenge is just that, when initially investigating this, we found several possible failure mechanisms, but the background information was incomplete and it wasn't clear the rate or extent that they would occur. And this is why experiments were necessary. And so I want to try to explain why we chose silicon as a storage material. And we can think about it by first considering salts, which are shown on the left. These are the main high temperature storage material used commercially, for example, in molten salt concentrated solar plants, where there's a large tank similar to this system but at lower temperatures around 560 Celsius. The reason we didn't choose salts is because we want to operate at higher temperatures, both to increase efficiency and to enable the use of this photovoltaic heat engine. But salts are a cost-effective option for energy storage. Another option is tin, which is very interesting. It's shown here. It has a very wide liquid range, so it melts at a low temperature and boils at a high temperature. It also has high thermal conductivity and low viscosity, so it's really great as a heat transfer fluid. The problem with tin is that it's between 20 and 40 times more expensive than the other two materials on an energy basis, and so it's too expensive to use for energy storage. So it has applications for heat transfer. And finally, silicon, while it has a high melting point, the cost is low and its very high boiling point means it's well suited for this application. So now I want to walk through the full-scale system concept, and the reason this is important now is because it was used to develop the economic model. So to determine the cost of components, I needed to look at the full-scale system to determine the amount of insulation, tank material, et cetera, that would be needed. And so if we start at the top left going clockwise, we look at the graphite heater. These U-shaped heating elements can be made from graphite or tungsten, and electricity is passed through them just as with a commercial oven, like a residential oven, and it generates heat, which is radiated out at pipes containing silicon. So there's heat transfer between the electrically heated resistors and the silicon. And the key equation that was used to develop this heater was the radiative transfer between the two, because this determines how hot the heater gets. And the heater is actually the hottest component in the system, hotter than 2400 Celsius, because it needs to be able to transfer heat. And so this equation is just radiative heat exchange. And what it showed is that the heating element needed to be about 2500 degrees Celsius in order to heat the silicon to 2400 degrees Celsius. Going to the next part of the image, we have the tank wall. And so you can see these individual elements, they're about 1 meter in size for a 20-meter diameter tank. And this is because this is about the largest size that graphite is manufactured. It wouldn't be practical to make the entire tank out of one piece. So instead, we have individual components that are bolted together using carbon bolts. And so a key equation used in this case is the stress developed in the wall by the pressure of the fluid from gravity. So the wall has to restrain that. And then for the insulation thickness, we looked at how thick the insulation needs to be based on its thermal conductivity and the amount of heat you want to lose per day. And so there's a trade-off here between the cost of insulation and the amount of energy loss. And so I left this heat flux as a variable and optimized it based on the overall cost of electricity output. This resulted in a heat loss of about 1% per day when you're storing for about a day. So 24 hours of storage, you would tolerate or ideally have 1% of heat loss per day. And this results in insulation about 1.5 feet thick. The next is the pump, which geometrically is just a centrifugal pump that's located in the bottom of the tank and pumps silicon out to the heater and the heat engine. And finally, the heat engine, if we look at the detail image on the left, we have these blue surfaces, which are photovoltaic cells, and they're exposed to very high intensity radiation coming from the silicon, which heats these pipes, which heats these fins, which are made from tungsten, emitting light at the PV cells. So that's how we convert back to electricity. Now, using this model, I developed a cost model for the system. And if we look at the first bar chart on the left, we have the cost of energy storage. So this is the storage components instead of the conversion or power components. So this first chart, you can see the orange section is the silicon medium. This is the storage material itself. And it makes up the bulk of the cost when the system is large, because this is by far the largest volume in the system. The second most important cost is insulation, and that's because at these high temperatures, there's only one type of insulation that can be used, which is porous graphite or graphite felt. And not only is it expensive, but its thermal conductivity is relatively high, so a lot of it is needed. The other most important costs are the construction and the tank wall itself. Now, this vertical axis is in dollars per kilowatt hour, and something you could use as a baseline to compare this $35 to is the current cost of batteries, which is around $200 per kilowatt hour, and expected to decrease to around $150. So this is significantly cheaper than batteries. The next bar shows a potential cost savings if the storage medium was changed from silicon to iron. And the reason this is cheaper is both because iron itself is inexpensive, but also because its volumetric energy density is higher, which means the rest of the system shrinks for the same amount of energy stored. The problem with iron is that it also reacts with carbon, the graphite tank, but it doesn't form a protective silicon carbide layer, and so this reaction would continue until failure. However, we wanted to investigate whether there's a mixture of silicon and iron that could be used, which would mean that there could be some cost between these two extremes. Going on to the other plot, which is the cost per power, this is primarily the heat engine, the conversion from heat to electricity, which is in this case photovoltaic cells. The cells themselves are the cost in blue at the bottom, which are relatively low, not because the cells are inexpensive, but because the power density is so high. So essentially, this would be like putting a solar panel very close to the sun, where the heat has not diffused away into low intensity that we have at the Earth. And so these solar panels, these photovoltaic cells, generate electricity about 1,000 times more compactly than existing photovoltaic cells. So while they're expensive, you don't need as many of them. The other important costs are cooling the cells and converting from DC to AC electricity. In this last graph, the only difference is the manufacturing method for the cells, which could reduce the cost of the cells by about a factor of 5 if the substrates that the cells are grown on could be reused basically 5 times more frequently. So with this cost basis, we then wanted to look into what is the efficiency of the system so that we could compare it to other technologies. And I'm going to walk through the different lines on this graph. So the y-axis is efficiency, and the x-axis is different loss mechanisms throughout the storage cycle. So first we have the heater, where we convert electricity to heat. If you follow the solid red line, you see that when we convert electricity to heat, we don't lose much energy. And then when we store the heat for about a day, we lose 1%. When we pump it and have other auxiliary losses, just another few percent, while most of the losses are in the heat engine. And this is typical for any power generation technology. Most of the heat rejection is from the heat engine. And this results in a round trip efficiency of just over 50% for this TEGS technology. You could compare this to the solid black line, which is for existing molten salt energy storage systems, like for concentrated solar power. Now these operate at lower temperatures. So during the first few parts of the cycle, they're very similar, but at the end, the efficiency of the heat engine is lower, in large part because the temperature is lower. Now the dotted lines represent another type of quantity, which is called exergy, or availability, can be thought of as the usefulness of the energy. And the reason this is interesting to show is because of the difference between TEGs and existing storage technologies at lower temperature. So if we just look at this first interaction with the heater, in the TEG system, when we convert from electricity to heat, we only lose 10% of the usefulness of the electricity, and this is because the temperature is so high. This is why the possible efficiency of this storage system could be up to 90% if we had an ideal heat engine. On the other hand, when you're only storing around 600 degrees Celsius, you lose 40% of the usefulness just from that first conversion, which limits what you can do downstream. And this is one of the reasons that the TEG's high temperature system is so appealing. Now this graph shows a comparison between TEGs and other existing energy storage technologies. The y-axis is levelized cost of storage, which is in the same units as your power bill, dollars per kilowatt hour. So the average in the US is 6 cents per kilowatt hour. And that's a good metric to try to compare the cost of storage, because storage is an added cost. So you really don't want it to be any more than the existing cost of electricity, at least. So we can just look at a few technologies on this graph. The first is in red, which is the expected future cost of lithium-ion batteries. This is $150 per kilowatt hour and an estimated 10 years life. You see what happens is, as you store for longer durations, the cost of the batteries goes up. And this is because for batteries, there's just a single unit, the battery. It has a fixed relationship between its energy storage capacity and its power capacity. And so as you go to long durations, you start to underutilize the power capacity of the battery, and the cost goes up. This is in contrast to TEGs or other technologies where the storage and the power components are separated. So in TEGs, we have a tank, which can be any size relative to the heat engine. And this means when you need more hours of storage, you just make the tanks bigger. This is mainly why TEGs and pumped hydro have longer, can be used at longer durations affordably, and why their optimum or minimum cost is at a longer duration. So what this plot shows is that TEGS is affordable essentially out to about 20 hours if just silicon is used. And if some iron could be used, it could become affordable out to even over 100 hours. Now, while the previous plot showed a comparison between technologies, it didn't show the effect of efficiency. And so I made this new method to try to explain that effect. Here, we're looking at profitability instead of just cost. So on the previous curve, it doesn't really show you if any of those technologies will actually be deployed because it doesn't compare their cost to their potential revenue. So here we consider arbitrage as the revenue for energy storage. Arbitrage is when you buy electricity or any other good at low price and then sell it at high price. And so this plot on the top left is actual data from the Pennsylvania, New Jersey, Maryland grid in 2009, based on the variability of electricity prices. And it tells you what an electricity storage system could have made in profit from operating on this grid. And so the y-axis is arbitrage value, which is essentially in units of dollar per size of the system. And the x-axis is efficiency. So you see that the more efficient the system is, the more money it can make. And this is because it has to purchase the electricity. So if you look at the intersection of 36% with the y-axis, this means if the system is less than 36% efficient, it doesn't earn any money by participating in arbitrage because it has to buy so much electricity that by the time it sells it, it actually doesn't earn as much as it paid. And so efficiency is important, and also the duration of storage is important, which in this situation was saturated around 10 hours. You see there's a big difference between 3 hours and 10 hours of storage, but a small difference when we go up to 20 hours. The table on the bottom was just used as the cost inputs to the main figure on the right. And so the way this figure can be read is if you pick a technology like TEGS, look at the white circle, its location is its cost. So it's about 30 cents per watt for the power system components and about $40 per kilowatt hour for the energy system components. Now the location, the color of the background in that location tells you the efficiency that would be required for the system to be profitable. And by profitable, I mean to reach at least a 10% return on investment. This is the internal return on investment. So TEGS can be profitable because it's around 50% efficient, but it only needs to be 35%. On the other hand, if we look at pumped hydro, this triangle shows that the efficiency of pumped hydro would be required to be 65%. And in fact, it is 80%. So this technology is also profitable, which is why it exists. This plot is useful because it shows that these three technologies are the only long duration energy storage technologies that are currently profitable, as opposed to batteries and flywheels. Because their capital cost is so high, they're actually not on this chart because they would be off to the right because their costs are too high. All right, so with that economic motivation in place, we moved into some of the technical issues. And the first is just how to reach these high temperatures efficiently. And mainly the challenge that comes in is how to electrically isolate the heater. So first I made a SolidWorks model of the heater system, which is shown on the left. You can see the heater, which is this thin plate connected to tungsten conductors that provide the electricity. And just above it is just a graphite thermal mass where I'm measuring temperature. The thermal model is on the right, which shows the temperature profile. And then at the bottom, we have the transient temperature profile, which shows that the thermal mass of the insulation is actually so significant. This test has to run for about 10 hours to reach a nearly steady state. Now, in selecting the heater material, there are really only two material candidates that conduct electricity and remain solid at high temperatures above 2000 Celsius, and these are graphite and tungsten. There's two material properties I'm showing here that can be used to try to pick a heating element material. The first is the resistance. So for a heater, you want kind of a medium resistance. It needs to be resistive enough to generate heat, but not so resistive that no electricity can flow. And so tungsten and graphite resistance values are both tolerable. The problem with tungsten is that its resistance changes drastically between room temperature and high temperature, and this causes the heating element to perform differently. And so this makes it a more complicated material to use. The other property I'm showing here is vapor pressure, and this is an indication of the rate that the heater will evaporate when it's hot. And you can see that graphite across the temperature range, and especially at 2500 degrees Celsius, evaporates or has a vapor pressure about 10,000 times higher than tungsten. Now, although it's much higher, graphite can still last several years. You lose about a millimeter of material per decade, but it shows you that tungsten is definitely preferable from an evaporation standpoint. And so in these experiments, we tried using both materials. So the next thing to consider with the heater is how to electrically isolate it. So first, using a tungsten heater shown here, it's this thin heating element that needs to rest on a surface beneath it that doesn't conduct electricity. And so these curves shown here are different materials' electrical conductivity versus temperature. And I wanted to select a material that was resistive, much more resistive than the heating element itself, at up to 2,500 degrees Celsius. But as you can see, most of these curves stop well before that temperature because the materials decompose. And so hafnium oxide, was the only candidate material that has been determined to survive at least nearly to this temperature, around 2,300 degrees Celsius. And so we tried using this to separate the heater from the electrically conductive materials around it. However, in this experiment, these hafnia discs actually melted. Or they appeared to melt, but what happened was that because of the presence of carbon, both the surface the hafnia was resting on and also carbon vapor that evaporated from the high temperature heater and insulation surrounding it, the carbon oxide that can form is more stable than the hafnium oxide. And so at these temperatures, the hafnia ceramic was reduced to a metal, which has a lower melting point, which caused it to melt and then become conductive and cause the heater to fail. The way you can think about this is the stability of hafnia versus carbon monoxide, which are the two oxides that are competing here. This plot on the right is called an Ellingham diagram and compares the stability of different oxide materials. And so the lower a material is on the vertical axis, the more stable. This means it has a larger negative Gibbs free energy. And so carbon monoxide is this downward sloping red curve, and you see that as temperature increases, it becomes more and more stable, unlike all the other materials which become less stable. And because of this, around 2,000 degrees Celsius, even the last stable oxide, which would be hafnia or magnesia, become unstable in the presence of carbon monoxide, and that's what we observed in this experiment. So instead of trying to put a solid between the heater and the base beneath it, we just used a more rigid heater material, which was graphite. The reason it's more rigid is that its resistance is higher, so it can be made thicker. This isn't necessarily a problem at the large scale, but was a challenge at the smaller scale we're doing experiments at. And so we used this graphite heater that was just suspended by these tungsten rods, and therefore we avoided the need for a 2,500 Celsius electrical insulator. And then we were able to reach higher temperatures around 2,000 Celsius when another problem occurred. And this was electricity traveling through the gas. So now there's no solids for electricity to arc through, but it actually, as you can see in this video, traveled through the argon atmosphere into the electrically conducting insulation above and then back down to the other side of the heater. The problem with this is that the resistance reduces when this happens, which reduces the heating and puts a limit on the overall temperature. But it also causes the heater and the lead rods to the heater to slowly degrade. They sort of melt because when electrons are emitted, the bonds between the graphite atoms become weaker. And so this was a problem both for heating and just the life of the system. And so we needed a way to prevent arcing. So first we tried to understand why it's arcing in the first place. And one key equation to look at is called Richardson's law. This shows that the thermionic current density, which can be thought of as like the current, like the amperage flowing out of the heater through the gas, is equal to the temperature squared times the exponential of the work function and also related to the temperature. So you see the two key variables here are the work function of the material, which you would want to be high to avoid arcing, and the temperature, which you would want to be low to avoid arcing. However, the temperature is fixed in this case, and the work function of the two candidate heater materials, tungsten and graphite, are very similar, around 5 electron volts. So this equation predicts that we would have about 1,000 amps of arcing for the size heater we have, but it relies on assumptions that are not valid in this case. So it assumes that there's a vacuum, whereas we had argon gas. It assumes there's no electric field present, which you actually are applying voltage to the heater, so we could actually even get more arcing. But it also neglects the space charge effect. Space charge effect is basically when an electron is emitted from a surface, the second electron is influenced by the previous electron. And since electrons repel each other, it's repelled back to the surface. And so the space charge effect is a very important effect that mitigates arcing. The arcing current is also limited just by the current we're providing to the heater. So for example, if you heated up a material not connected to any electricity, it would emit a few electrons, but then become so positively charged that no more electrons could be emitted. But in this case, we're supplying current. And like I said, the emission is also reduced by the space charge effect, which there's another equation called Child's law, which estimates this effect, where the current density is equal to a relationship between the voltage and the distance between the heater and the thing it's arcing to, which is the insulation. So this gap is about an inch. Because this gap is quite large, this equation predicts a current density of only 0.1 amps for this size heater. And so really what we get is something between the two, but it just shows that neither of these equations are really completely valid for our situation because we have a gas present. And so the gas can act as an arc suppressant or an arc enabler, depending on the type of gas and the temperature. So one way the gas can cause more problems is if you get an avalanche effect where one electron is emitted, it hits a gas molecule and knocks off 2 or more electrons from that gas molecule. And so you can actually amplify the current in this way, causing a cascade breakdown, which is indicated by this figure here. So depending on the gas, the arcing can become better or worse. Now, arcing is a problem at low temperatures too in high voltage electronics, and the way they mitigate it is by using a arc suppressant gas called sulfur hexafluoride. The reason this suppresses arcing is because it's this large molecule that's highly electronegative. It can handle absorbing 2 more electrons per atom, per fluoride atom. And the result is when an electron is emitted from the graphite surface, shown in black here, it can be absorbed by the sulfur hexafluoride, which moves very slowly because of its high mass, but also becomes negatively charged, helping to repel further electrons back to the surface. The problem with sulfur hexafluoride is that it's not stable at high temperatures, and when it decomposes, sulfur and fluoride react with the system we have. And so we couldn't use that material. However, considering that we started with argon, the only stable material left on the periodic table that we can use to reduce arcing is helium. The reason helium is better is because it's a smaller atom with fewer electrons and one fewer shell of electrons. For helium, the ionization energy, which is the energy to remove an electron, is larger than it is for argon. It also has a less negative electron affinity. Both of these result in helium being less likely to have both of its electrons stripped away when hit by an incoming electron. And so helium was expected and has been measured before to be relatively stable under arcing conditions compared to argon. And so in experiments, we found that helium doubles the arc initiation voltage, which means that if we use helium, shown in blue, we can operate at twice the voltage compared to using argon. The downside of helium is that it's far more thermally conductive than argon, which means we have a lot more heat loss from the system. So while I used helium in these experiments to enable heating to high temperatures, in the full-scale experiment, it most likely is more optimum to use argon and mitigate arcing in other ways. So there's a few other methods we used to reduce arcing. One of them was just to remove the sharp corners from the original heating element, because these increase the electric field gradient. And so this reduced the electric field by about 25% and allowed us to operate at higher voltage. But the more interesting method was to account for the non-symmetric electric field that's present in heaters generally. So if you see this figure in the center, there's no electric field on one side where the heater is at the same voltage as the surroundings. But on the other side, there's a large electric field, which is at the peak voltage difference. If instead we connect the center of the heater to the insulation, now one side becomes charged negatively and the other side positively, but the total voltage difference, the maximum voltage difference, is now half, which means that we can operate at twice the voltage under the same arcing conditions. So this change alone enabled us to operate at twice the voltage, which results in much higher power. So those methods put together enabled heating above 2000 degrees Celsius without any active cooling, so the heat loss was low. And with the heating system in place, I moved on to some of the materials compatibility issues. In this next section, I'm going to go through the effect of graphite pore size, the effect of impurities in silicon, and the effect of this non-isothermal circulation. So the challenges to containment that we predict is, first of all, silicon and carbon react to form silicon carbide. This has been known, and it's also known that under some conditions, this reaction forms a thin protective layer through which carbon and silicon diffuse so slowly that the reaction is slowed down drastically, even for a thin layer, a few microns thick. However, if the graphite has large pores, the silicon may leak out of the containment before the pores are filled by silicon carbide. This can also cause the graphite to crack as it's bulk converted to silicon carbide, which results in a volume expansion. Another problem is that the impurities in silicon could react with the graphite or cause the graphite to dissolve more. And the next biggest problem is that silicon dissolves carbon. So this is true of all liquids contained in solids, just to varying extents. This equation shows that the solubility, which is X, which is a number between 0 and 1, is related to the bond strength, which is indicated here by the formation enthalpy, and the difference between the temperature you're at and the temperature that the material melts or decomposes. So here we're considering silicon carbide because that's the surface the silicon is exposed to, which decomposes up here at 3100 Kelvin. So we're not that close to melting or decomposition, but this curve shows the effect of the solubility. So as you increase temperature, solubility increases. So we're operating at a peak temperature of 2400 Celsius, which is about 2700 Kelvin, which is right here. What you see is where this temperature intersects this solubility curve shows that carbon is 5% soluble in silicon at this peak temperature. And while that's a problem, the bigger problem is that this solubility is different than the solubility at the lower temperature in our system, which is around 1%. And so that means in the cold tank, 1% of carbon could dissolve, but then when the silicon is pumped into the hot tank, another 4% could dissolve. But then when the silicon is pumped back to the cold tank, the excess carbon could precipitate out of the liquid and deposit in the cold tank. And so this cycle could cause material loss from the hotter sections of the system. Now, this could obviously be a problem. The phase diagram doesn't tell us for sure whether it will actually occur over the lifespan of this system, because this is just what would happen after infinite time. And so we were wondering if maybe the silicon carbide layer that forms could protect the graphite from dissolving, or at least slow down the dissolution. So for the first set of experiments, I designed a small system which consists of a tank that's about 4 inches tall, made of graphite, shown on the left, filled with silicon and heated by an induction furnace, which electromagnetically heats the system contained within insulation. This is a small, relatively simple experiment for determining the effect of pore size, silicon purity, and thermal cycling. So the way these experiments were conducted, I started with a tank that was about 4 inches tall. It's made from 2 pieces and sealed together, not out of necessity, but to demonstrate the ability to seal. And these tanks were bolted together with these carbon fiber bolts shown here. The system was heated, usually to around 2200 degrees Celsius for several hours, and then removed from the system, cross-sectioned, and looked at with a scanning electron microscope to see what happens at the interface between the silicon and the carbon. And so this figure in the bottom right shows that we have graphite, and then a thin layer of silicon carbide, you can see is about 20 microns thick, and then silicon. And this is exactly what we want to see. We know this happens at lower temperatures from previous reporting, but this was at up to 2300 degrees Celsius. The silicon carbide layer remained attached and protected the carbon from further reaction with the silicon. In these tests, I also put a bolt in the silicon in order to determine if it could survive the contact, because the full-scale system has bolts on the inside and the outside of the tank. And the bolt also formed silicon carbide layer and didn't exhibit any strength loss. I also made a tank that is about 2 gallons. So this is about 8 inches on a side and the height, and heated it up to 2200 degrees Celsius for 4 hours. Silicon was also contained in this case, and silicon carbide not only formed on all the submerged surfaces, but also on the surfaces above. And this is because the vapor pressure of silicon is relatively significant at these temperatures, just a few pascals, and the diffusion path to these surfaces is relatively short. So silicon actually evaporated and deposited on these other surfaces, reacting and forming a silicon carbide protective layer on all of these exposed surfaces. Now, the first question we want to answer with regard to these experiments is what is the effect of graphite pores, and specifically the effect of pore size? So first I wanted to try to estimate this effect. And I did this with just a simple mathematical model comparing the driving force for silicon to leak out of a pore, which is shown in red, to the reaction of silicon carbide, which is closing the pore. So silicon is pulled through the pore by capillary forces much more strongly than gravity pushes it, because the pores are small and silicon wets graphite. And so that was the main driving force for the silicon flow, which is indicated by the first equation, looking at the velocity of silicon, which is driven by surface tension and resisted by viscosity. The second equation is the velocity of the silicon carbide layer. And so this is basically the reaction rate, which is the main resistor of which is the diffusion of silicon or carbon through the silicon carbide layer. And so it's represented by this scale, the diffusion coefficient divided by the thickness, which is the radius of the pipe approximately. Now, combining these equations, I can estimate the critical radius if I choose a maximum length that we would tolerate silicon leaking. So setting that to 10 millimeters, which is thinner than the overall tank wall in the full system, which is about 100 millimeters, we find that the critical radius is estimated to be around 0.3 microns or 0.6 micron diameter. So considering the rough order of magnitude of these equations, we estimate that a critical pore size based on diameter would be about 1 micron. So then I ran some experiments to validate this. First, we ran experiments with very low quality graphite, which have large pores greater than 10 microns. And so we expected these to fail or leak, and in fact they did. And these are the figures shown at the bottom here. On the left, you can see a tank that essentially exploded because of the reaction between silicon and graphite. It happened so thoroughly. So there's so many large pores that silicon not only leaked through the wall, but also converted so much of the graphite to silicon carbide that the graphite itself broke. The figure on the right shows a different scenario where a different grade of graphite resulted in leaking, but no mechanical failure. And so in the SEM image shown on the far right, we can see silicon, the graphite wall, and then on the far side of the graphite wall, we see this gray material, which is silicon again, which shows that silicon traveled all the way through the wall. You could also see silicon dripped on the surface beneath this tank after the experiment. And so this showed that, in fact, pores greater than 10 microns definitely cannot contain silicon. Unfortunately, they don't make graphite with pores between 1 and 10 microns because of the discontinuity between manufacturing methods. So the next set of graphite materials had pore sizes between 0.1 and 1 micron. So essentially, we would predict all of these to pass, or at least most of them with pores smaller than 1 micron. And in fact, in these experiments with 4 different grades of graphite, with pores between 0.1 and 1 micron, they all successfully contain graphite, forming a thin silicon carbide layer shown in these SEM images on the bottom. This medium gray color is silicon carbide. And so this showed that basically any pressed grade of graphite, which has pore sizes up to 1 micron, can be used to successfully contain silicon even up to 2300 degrees Celsius. This is very important because these grades of graphite are just a few dollars per kilogram, between about $2 and $7 per kilogram, whereas very high quality grades of graphite can be up to $1,000 per kilogram. Now, the next question to answer is, what is the effect of impurities in the silicon, which determines the cost of the silicon? So the challenge here is that high purity silicon, like 99.99% pure silicon, electronics grade, is far too expensive, again, around $1,000 per kilogram. So we needed to use a much less pure grade, which is usually referred to as metallurgical grade silicon. This silicon is around $2 per kilogram, and so it's affordable. And that's what we used in these experiments. And what we found is that the impurities did not cause any problems. The main impurities are iron, calcium, and aluminum. And so calcium mostly evaporates, the iron remains suspended, and so does the aluminum. And so these did not inhibit the formation of a silicon carbide layer. And in fact, we also wanted to investigate, as I mentioned in the economic section, the effect of adding iron to reduce the cost even further. And one way to predict the effect of adding iron is looking at a phase diagram. And so this is called a ternary phase diagram, where we look at the effect of 3 different materials. This is at a single temperature. And so the different lines just indicate the concentration of different materials. So for example, on this horizontal axis, we're just going from 100% iron to 100% silicon. And so we've looked at that phase diagram before. We see that at 1450 Celsius, the solubility is low as long as the concentration of iron is less than 50%. But when we reach higher temperatures, this solubility increases. Now this red curve is an estimation based on the 2 points shown, since a ternary phase diagram was not available at these temperatures. But what this shows is that definitely as you add iron, the solubility of the solid carbon in the iron silicon mixture will increase. And so if it's not protected by the silicon carbide layer, adding iron will only exacerbate the dissolution issue. However, when I tested iron in these small tanks under isothermal conditions, this was without the non-isothermal circulation, we found that we could contain up to 2/3 iron by mass. And this is really important because this reduces the cost of the system by 2/3 essentially, because iron is so cheap and its volumetric energy density reduces the size of the system. So this first figure shows an iron silicon mixture that's 2/3 iron contained in a graphite infrastructure, silicon carbide still formed at the interface, and an added benefit is that it actually shrinks slightly on freezing because iron shrinks and silicon expands, and the net effect was a slight shrinkage at this concentration. So this prevented the tank wall from breaking on freezing. So this is a pretty great mixture. When we use more than 67%, for example, 80 or 90%, we find that a silicon carbide layer does not form, and in fact, an iron silicide, FeSi, forms at the interface, and a lot of the carbon wall was dissolved. At 90%, we could observe a lot of carbon in the liquid itself that precipitates out on cooling. And finally, if pure iron was used, we see that the tank wall actually dissolves up until the point that the liquid is saturated with iron. And so this was very important because it showed that we could actually dilute the silicon with 2/3 iron. Now, the next challenge to investigate was the effect of non-isothermal circulation. And so because we've shown that carbon has a temperature-dependent solubility in silicon, if the silicon carbide layer doesn't prevent the carbon dissolving, then I modeled the effect of this dissolution in COMSOL and estimated that we would lose about 1.2 millimeters of the wall in the hot zone of graphite and over the course of 4 hours. So if this happens, this means that the graphite is dissolving very rapidly, which would prevent the system from lasting the years needed for commercial application. The way I tested this simply was just to use a tall tank and heat the bottom of it to induce natural convection. So the bottom of the tank was about 500 degrees hotter than the top. This causes silicon to heat up and become less dense, float to the top, then cool off and float back down. This results in circulation from the hot zone to the cold zone. And when I apply a mass concentration boundary condition based on the solubility of carbon and silicon, this model predicts, like I said, the 1.2 millimeter loss over 4 hours. So I ran an experiment based on the temperature conditions in this model and found that, in fact, carbon does dissolve at almost this rate. So we predicted 1.18 millimeters, and I measured 0.82 millimeters loss. The reason the loss is slightly smaller is most likely because the carbon that dissolved, when it redeposited in the top of the tank as a solid, it started to block the flow path and reduce the convection currents. But what this shows is that, in fact, carbon does dissolve despite the presence of a silicon carbide layer. And this is a major issue for this technology because there's no way to really avoid the non-isothermal circulation when we need to move silicon from the hot tank to the cold tank in order to use the energy stored. One other issue we investigated was the effect of just transient thermal cycling, so heating and cooling of a single material, which is relatively spatially uniform. The reason this might cause a problem is that silicon carbide and graphite have different thermal expansion coefficients. So silicon carbide expands less with temperature. So when the system is heated, silicon carbide is loaded in tension, and because of the 500-degree temperature gradient, this results in a stress of about 200 megapascals, which is greater than the tensile stress of silicon carbide. So we wanted to investigate whether thermal cycles cause the silicon carbide layer to delaminate, which could be seen by material loss from the graphite. So if the layer delaminates, then a new layer would form. And so after about 25 thermal cycles, it should just be visually obvious that the layer is dissolving or delaminating because of the 0.25 millimeter thickness loss. And so in this experiment, you can see the temperature profile on the left was heated from 1600 to 2100 degrees Celsius about 22 times. And in fact, after one cycle, no material loss was noticed, but after 22 cycles, there was anywhere from 0 to 3 millimeters, where 3 millimeters is the total wall thickness of material loss, depending on the location. And we can also see these flakes shown in the middle figure, which indicate delamination. And so, in fact, this experiment shows that it's possible for thermal cycling to cause delamination, although this thermal cycling was so fast, on the order of 15 minutes per cycle. It's possible that slower thermal cycling could avoid this issue, but it's at least an issue that needs to be further investigated. And finally, the last question, which with regards to the effect of pumping, whether it causes delamination, abrasion, or the pump getting stuck when the silicon carbide forms. And again, the reason a pump is needed is because there's different system components that are only connected by piping, which is only used if a pump is available. So to design the pump, I used existing design for centrifugal pumps, except for the initial experiment. To simplify it, I wanted to operate at low speed, a low RPM. And so I designed the pump with forward curved blades, whereas most centrifugal pumps use backward curved blades. The benefit here is that the fluid accelerates both radially and circumferentially, and this causes a greater pressure rise at a given pump speed. And so I modeled this pump in ANSYS and found that at 300 RPM, I would develop the 100 millimeters of pumping head needed, although the pump would be operating at very low efficiency because of its low speed. And so at low speed, a centrifugal pump doesn't have enough velocity for the inertial effects to outrun the viscous losses. So running the pump at higher RPM would resolve this issue. But in fact, the low efficiency, even at the large scale, is not a big issue because the energy density is so high that we can tolerate an inefficient pumping system around 10% efficiency. So now that the pump geometry was designed, I needed a way to verify its functioning. And the way to do this is to measure its flow rate, but we couldn't use any commercially available technology because it's far too hot. So we designed a very simple flow meter, which is essentially a tank with a hole in the bottom of it, sometimes called the leaky bucket method. And so when silicon or any fluid is pumped into the tank, it flows out of the bottom, but the height of the fluid in the tank is related to the incoming flow rate, because the faster the incoming flow rate is, the more pressure is needed to push the fluid out of the bottom of the tank. And this pressure comes from the gravitational pressure, which is related to the height of the fluid in the tank. This is well modeled by Bernoulli's equation, where the pressure is the same at the top and bottom surfaces because they're free. And so we're just comparing the velocity to the gravitational driving force. And so we can solve for velocity, which is proportional to the mass flow rate. And we find this relationship where the mass flow rate is equal to a constant times the square root of the mass of the tank, because the mass and the height of the tank are related. So with this relationship, we can measure the weight of this tank and determine the flow rate. To further simplify the system and reduce heat loss, I made the pump and the flow meter a single component. So you see here in light gray is the impeller that rotates. The fluid comes in, is slung outward by the impeller, and flows through this path to the top of the pump, and then falls into the container on the top of the pump. And so here, as I pump faster, this green fluid level will rise to the second level, depending on the flow rate. And then the fluid leaks out of this bottom hole. So in this case, all I need to do is measure the weight of the pump to determine the flow rate. So when I stop pumping, the pump will get lighter. When I start pumping, it will get heavier. And I can actually experimentally determine the exact flow rate based on this information. So first, I ran a test with water to determine the effect of this. So I lowered the pump into water, turn it on, it fills up with water, it gets heavier, turn it off, and the water drains out. And it's while the water is draining out that I can calibrate the flow meter. So if we look at this curve on the bottom left, this is just raw experimental data of the mass of the pump versus time. So it's decreasing as the water drains out. But since I now have mass versus time, I can take the numerical derivative and get mass flow rate versus time. And with mass flow rate versus time and mass versus time, I can plot mass versus mass flow rate parametrized by time. And now this is the exact relationship I want, where I can read off mass. So if I have 400 gram mass in the pump, this tells me the flow rate is 10 grams per second, just based on conservation of mass and Bernoulli's equation. You can see that this experimental curve matches very well to the expected shape based on Bernoulli, where the mass flow rate is proportional to the square root of the mass. So with the pump and flow meter designed, I needed to design a system to mount the pump and actuate it, cause it to rotate. And the main challenge here is that the pump is going to be above 2000 degrees Celsius, while the motor and the electronics need to remain below 100 degrees Celsius. So there's a 2000 degree temperature difference between the two. And the way I bridge this is by connecting them over a relatively long distance with as low thermal conductivity materials as possible. And so the pump is mounted with these hollow tubes shown here, which at the bottom are graphite and where it's colder are ceramic. And inside this tube is a carbon fiber bolt. So when these bolts are tightened, the pump is held in place. However, when the pump is heated from room temperature to 2000 Celsius, these sleeves, these hollow pipes expand vertically about 5 millimeters, while the bolts don't expand much at all. And the effect is that a large stress is developed. And so this is accommodated with the springs shown here that are in series with these pipes. So when the pipes expand, the springs are compressed. And this prevents a large stress from developing. The pump is actuated by a low thermal conductivity zirconia shaft connecting the pump to the motor, and both of the components are mounted to the same plate that's water cooled. And this is just a zoomed in view of the thermal profile and the pump mount. So this rectangle here is a metal mount with water flowing through it. Below is the pump. So the pump is bolted to this, but there's these cooling channels shown on the right that geometrically separate the hot zone where the pump is mounted from where the motor is mounted. And this keeps the motor cold well below 100 degrees Celsius. Another thermal profile is shown here, which is of the pump and the tank enclosed within about 1 foot of insulation. And you can see that, most importantly on the right, even within the pump, which you would expect to be relatively isothermal because of the high thermal conductivity of graphite and the silicon, it actually experiences about 100 degree temperature gradient from the top to the bottom of the pump. And what this means is that we could experience the same dissolution, non-isothermal circulation issues that we saw in the previous experiment, where graphite is dissolved in the hottest area and then deposited in the colder area. So putting it all together, we have the pump in the very center of this figure, which is above the tank, which has silicon in it. Once the silicon is melted, the pump is lowered in by some linear actuators and then turned on. This whole system is operated inside an inert environment of argon or helium inside the chamber shown here, and the temperature is measured with a pyrometer shown on the left. The heater is shown on the bottom right. This figure shows what happens when the pump system is heated up and why the springs I mentioned are so important. So on the left is the system when it's cold. The springs are not compressed very much. And on the right, the springs are compressed almost completely because of the axial expansion of the ceramic and the graphite beneath it. You can see the color here is the heated pump system radiating light because it's so hot. This exposed surface that's white at the bottom here, it's only about 1200 degrees Celsius. The pump is much hotter, but about a foot lower in the insulation. So with the full pump system designed, we wanted to try to estimate what would happen when the pump was lowered into the silicon, because we know that this reaction will happen forming silicon carbide. And this is the first time we're putting dynamic components into silicon, which means we need motion between this light gray impeller and the dark gray pump body, but silicon carbide will be forming on both surfaces that are very near each other, and potentially the silicon carbide could cause the two surfaces to bond. And so we're thinking the best we can do is probably to have this layer form slowly. One way to make it form slowly is to try to have it coated by gaseous silicon, so silicon that evaporates from the liquid and travels up into the pump body, just as it did in the experiment with the large tank. The problem here is that the flow path of the silicon is very tortuous. It's a narrow, long flow path. The gap is only about 100 microns. And so if we estimate how long this would take based on mass transfer, it would take about 3 days for a 10 micron layer of silicon carbide to form. So essentially in these experiments, no silicon carbide layer formed via vapor coating. So we know we're gonna have to lower the pump into the silicon to cause this reaction. So at least one method is to lower the pump slowly so that while the reaction happens quickly locally, at least the entire surface isn't reacting at the same time. And this means that if any silicon carbide bridges the gap between the solid and the dynamic component, at least those few bonds can be broken. before more of them form. And this technique worked, except that in the first experiment, the pump wasn't lowered far enough into the silicon, but this actually gave us a very interesting insight into the mechanisms going on. And so we see that in this test, the pump shaft got stuck after rotating for a few minutes. And when I look into it with a scanning electron microscope, at the bottom of the sleeve, where it was lowered slowly into the silicon, we see a thick silicon layer between the two components, the pump body and the rotating shaft. And so this is what we would expect to see, and this is good. On the other hand, at the top of the pump, where silicon was introduced quickly because the pump speed was increased and silicon was forced up this passage, the layer is much thicker, the surfaces are very rough, and silicon carbide actually connects between the two components in several areas. And so this very clearly shows the difference between slow and fast silicon carbide formation. So in later experiments, we just made the sleeve of the pump shorter so that it could be fully immersed in the silicon. And this prevented the shaft from binding. So with these experiments pumping silicon, I was able to measure the flow rate just as I did with water. On the far left is the experimental drain curves. The center figure is just those three plotted at the same time. And then numerically differentiating and plotting mass versus mass flow rate, I was able to get this final curve, which again fits well to the square root behavior expected. And so when I measure the mass of the pump, I can determine its flow rate. Overall, silicon was pumped in 3 experiments over different durations, just a few minutes when the pump shaft got stuck, about an hour, where this test was ended because silicon leaked out of the tank for an unrelated issue from a design change, and finally 10 hours. At the top of this figure shown in gray are the phases of the experiment. So first we have shown in this hashed color the phase change time, and this is when the silicon is melting and then later when it freezes. So for example, in black, we see a large horizontal region here and another at the end of the test where silicon was melting and freezing. It's horizontal because there's a large amount of silicon and the phase change energy of silicon is large, the latent heat is large. And so regardless of the heat input, the temperature remains relatively constant during this period. So in the longest test where the pump was used for about 10 hours, or at least rotating, this test went on, but at the end of the test, the pump shaft got stuck, and throughout the test, the ability to measure the flow rate was degraded, and afterwards, it was very obvious what the problem was. So if we look at this figure in the center, this is the pump cut in half after the test. If we follow the flow path of the silicon up from the bottom, out to the side, and then up this path, you can see this path is completely clogged with silicon carbide. And so what was happening here was the same problem we saw in the non-isothermal circulation experiments, where the hotter section at the bottom of the pump was dissolving. Multiple millimeters of material loss was observed on the pump impeller, and then depositing in the colder regions. So not only was the pump dissolving, but it stopped functioning even sooner because the outlet was clogged. And we can see silicon carbide deposition all over the inside and the outside of the pump, with most of it at the top of the pump where it was colder. And so this is just another indication of the problem of dissolution because of the high solubility of carbon in silicon. Another way to view this is the 3 experiments shown next to each other, which shows the degradation over time. So in the short 0.1 hour experiment, we don't see much silicon carbide deposition. In the 1 hour experiment, we see that the outlet is partially clogged, and then finally, after 10 hours, it's completely clogged. And what this shows is that the pump and any other system component that's not isothermal is going to experience very rapid degradation compared to the timescales that the commercial system would need to last, which would be years. So overall, this shows that the material loss rate from non-isothermal circulation is about 1/4 millimeter per hour, which is far too fast for the system to tolerate. Now, while the pump could be made isothermal in a large-scale system, fundamentally the heat exchangers, like the heater and the heat engine, cannot be made isothermal. And so I tried to estimate what is the maximum solubility we could tolerate in a system like this to try to see if there's other materials we could consider. So if the loss rate is in meters per second, or time, distance per time, I set a maximum of 1 millimeter per year of material loss. And this results in a solubility, which is here, of 0.003%. This is 1,000 times lower than silicon, which shows why we saw such fast degradation. This equation is basically just mass transfer, including a convective enhancement called the Sherwood number, which is analogous to the Nusselt number for heat transfer. So I just used a value of 4 here, which is for laminar flow. The diffusion length in this case could be like the radius of a pipe. And so in this case, I use 50 millimeters. So we see that we need something on the order of 0.003 atom percent solubility. And one material that I mentioned earlier that has solubility even lower than this is tin. The problem with tin is that it's too expensive to be used for storage, but one option for the future of this technology could be to use tin as a heat transfer fluid and graphite itself as storage. So very low-grade graphite is actually even cheaper than silicon. The downgrade is that it's not a liquid, so it's a little bit more difficult to get heat in and out of it. But the system shown here, where you have some large graphite blocks that silicon is pumped through. So for example, in the charging case shown in the middle, if you pump silicon up through the heaters, it can be heated and then deposit that heat in the graphite. When heat is needed, the hot silicon can be pumped out and the heaters can be replaced with the PV cells generating electricity. Now, although the solubility of graphite in tin is much lower than silicon, it still would result in about 0.3 millimeters of material loss per year, which may be too much for decades of life. And one way to mitigate this is actually automatically implemented by the system shown here. So if we look at the charging case, the hot zone is at the top and the cold is at the bottom. So during charging, we could have material loss from the top and deposition in the bottom. But then during discharging, we would have deposition in the top and material loss from the bottom. And so this might serve to reverse the material loss, and this could cause the system to survive longer or have a lower loss rate than this predicted 0.3 millimeters per year. And so this is one alternative version of this TAGS technology that could be taken forward. So overall, I just want to summarize the contributions of this thesis to new knowledge that wasn't known before. So first of all, I developed a new economic framework for evaluating and comparing storage technologies, mainly focusing on efficiency as a key variable. And I did a techno-economic analysis of this technology so that we have an estimate of its cost. For electrical isolation, I just applied a few new techniques to passively cool a heater rather than actively cool it so that higher voltages can be used and there's less heat loss, which can result in a cost-effective, efficient heating system. And then I experimentally demonstrated this. I investigated the effect of pore size at temperatures up to 2300 degrees Celsius and showed that the critical pore size is somewhere between 1 and 10 microns. I investigated the effect of impurities, showing that metallurgical grade silicon can be contained successfully at 2300 Celsius and up to 2/3 iron can be used. But these conditions are only true if the system is isothermal. And so when investigating the effect of thermal cycling, I showed that under non-isothermal circulation, there's drastic material loss, whether the silicon is pure, whether iron's present, just because of the solubility of carbon and silicon. And so this is the key problem with this technology, is that when you pump between a hot and cold area, the graphite containment dissolves. This was also observed in pumping, despite the fact that from a thermal, fluid, and mechanical standpoint, the pump worked as designed. And at least this bodes well for a future material pair, such as carbon and tin, where there's no chemical interaction between the two. So we do know that it is possible to pump at these temperatures. And so if more compatible materials are used, potentially we can circulate tin at these temperatures in this alternative embodiment I discussed. And I'll just leave this summary slide up of some of the publications that are in progress and have been completed related to this work. And I'd like to answer any questions anyone has now.
Thanks, Caleb. I guess a virtual round of applause, as I heard it mentioned earlier today. This is a good spot to, I guess, take questions from the audience. So I'm not sure if the raise hand feature is allowed, but if possible, if anyone has a question, why don't you go ahead and raise your hand and then I'll call on you so you can unmute and speak. I'm not sure if anyone else can see any hands raised. Does anybody have a question? Maybe you can just unmute if you do. Wow, I guess everything was so incredibly clear. No one has any questions.
Excellent.
Let me ask a question.
Okay.
Sure.
Uh, Caleb, is an excellent presentation, and you said they look at the New Jersey, the electricity price, and when you do the modeling, technical economic.
Yes.
So if you use the estimation you have, right, the cost, have you looked at say the actual price fluctuation every day over the year and say what's the using the current price, what's the time to get your return of investment?
Okay. That's a good question. So this curve shown here in the top left is based on real-time electricity prices from 2009. Let me think for a second if I can convert that to time to payoff. The numbers are here to do it, but I haven't done that calculation. So the system.
Let me say, so the real price fluctuate about 5 minutes or something.
Yep, yep.
And so you assuming this will generate every 5 minutes to say that, say what's the response time you're assuming?
Okay, yeah, so for this technology, the response time, it depends what you mean, whether it's 0 to 100% power, but so if you think 0 to 100%, the time that is required to ramp that amount is just the time that's required to physically move the photovoltaic cells into the radiation. And so it can be done on the order of a minute or two. And then if it's changes that are, from 30 to 40% power output, that could be done on the order of seconds.
Yeah, so I guess my comment there, because the price change 5 minutes, right? The low price, maybe the 5 minutes that you capture, or if it's a 1 or 2 minutes to do what do you is that important or not?
Yeah, that's a good question. I mean, that is an area where batteries have an advantage because they can cycle, in milliseconds. But and it may be the case that you use batteries for the shorter duration fluctuations. But for example, when you have lots of solar and wind on the grid, the more common fluctuation is daily for solar and weekly for wind. But that's a good point. This technology, could potentially move faster. It's just that you're moving a cold component that's near a hot component. And so there's just some risk with moving it fast, but it's not fundamentally limited to a slow speed.
I have another question about the wall thickness between what's the diameter of the tube you assume or you use in particularly in the radiator section? What's the radiator to the cell? What's the geometry? What's the diameter?
Okay, so that's like this heater section shown here has a lot of these horizontal pipes. What we were considering was a 10 millimeter inner diameter, 20 millimeter outer diameter. So this is a 5 millimeter wall thickness. And it's actually that's an interesting question, because if you make the wall thick, like say we have a dissolving issue, so we'll make the wall thicker to resolve it. There's actually a big trade-off because the resistance through the wall, the thermal resistance is significant. Not because graphite is insulating, but because the heat flux is so high. So when you go from like a 5 to 10 millimeter wall thickness, you go from like a 10 to 20 degree temperature drop in the wall. So we're in a regime where you do need thin walls. And that's, that's the one.
That's a similar, that's the thickness that you use for the TPV system also, right?
Yeah, yep, yeah. Anywhere where there's heat transfer through the pipe, the wall thickness that we use is about 5 millimeters.
Yeah. What's the thermal conductivity you assume at that temperature range?
It's about 30 watts per meter Kelvin. So graphite's much more conductive at low temperatures, but at this temperature, it drops to around 30, maybe 35 watts per meter Kelvin.
Okay, thanks.
But yeah, it's an interesting question because we have these two trade-offs. We need heat transfer, but we don't want mass transfer. And they're both kind of driven by the same thing. And that's why you really just need a material change to get this to work. Silicon, the carbon is far too soluble in silicon.
Right. So actually, what's the flux again? At that say, let's say 2400 or 2200. What's the radial flux? What's the
Like the
silicon?
yeah, so like the black body flux is about 2 megawatts per square meter. In the heat engine, because the cells are reflective and only using some of that, the power generation is more like 100 kilowatts per square meter, but it's very high. Those solar panels only on the order of 100 watts per square meter electricity generation.
Mm-hmm. So what's the flux leaving the wall surface, leaving the going across the wall
of the pipes? It's similar, so it's on the order of 100 kilowatts per square meter. I guess it's a little bit lower because the area of the pipes is larger than the area of the PV cells.
Okay.
Caleb, maybe I'll ask one of my questions in the open session while people are thinking of other questions, and I leave the rest to the closed session. Since you're on this slide, have you thought about what the optimal size of this system is? Whether you're going to build it using the material you discussed, or because we need other material because of the issues you raised. So and the reason I'm asking is in terms of compatibility, would you build these systems kind of in a factory and ship them over and put them next to individual wind turbines, or would you have to build on location and with a farm environment? So
Okay.
Economy of scale and
right.
how you fabricate them might be an important factor.
Right. Yeah, so one of the downsides of thermal storage, and especially very high temperature thermal storage, is it has to be big to be cost effective. And so the system shown here, the reason we picked the size is this is where it becomes very cost effective at the 1 gigawatt hour of energy stored scale. So this is like a 20-meter diameter tank. You could make a 10 or maybe a 5-meter diameter tank and still potentially be profitable, but nothing smaller than that. And this is because the balance of plant costs become high. The cost of the tank walls, the cost of the insulation, the inert containment, all of these things scale with the surface area of the system, which increases less quickly than the volume. And so it's something on the order of 1 gigawatt hour that would be ideal. The gains from going from 1 to 10 gigawatt hour are only a few percent. And so, I mean, like you mentioned,
yeah, are you accounting also for the losses? I mean, I can sacrifice some efficiency if I want to go down in size.
Yep. Yeah. So in this model, so all these equations are plugged into MATLAB, and one of the things that's left as a variable is the heat loss rate in terms of like loss per day. So if you build a smaller system, like you mentioned, it's likely to be optimized to tolerate, maybe 5% loss per day. But that all goes into the final calculation, which shows that, it's not that it's not necessarily cost prohibitive to build a system at a quarter of the size, but it's definitely less profitable. And even at a 1/4 of the size, it's still too big to build this system modular and ship it. It's definitely the kind of technology that needs to be built in place. And of course that makes the initial demonstrations difficult. And it's a similar problem that nuclear has. But the materials are very cheap. And so compared to other alternatives, it's still pretty compelling.
Well, I guess, does this also apply for the heat engine? That engine doesn't seem to be the easiest to build on location.
That's an interesting question. So the heat engine could definitely be semi-assembled offsite, especially the cold side of it. So like this blue rectangular prism here that the PV cells are attached to is clearly modular. Each one I think is less than a megawatt, maybe 100 kilowatts. And they're like 100 millimeters by 100 millimeters by about 3 meters. So these could be made and shipped definitely. but the assembly, so like in the pipes shown here, like this array of pipes could be assembled modularly, but definitely the interconnection between these modules at least would have to be done on site.
All right. Thank you, everybody. Let's go ahead and attempt to do this breakout room thing. So I'm going to move. Well, I guess what should happen is everyone can stay where you are. The professors, in addition to Caleb, will probably get a message in a second asking you to join a breakout room. So we will go with Caleb to a breakout room, continue the discussion, and then you can wait here in this main room, and then eventually we will all come back and talk about, I guess, the final results of the evaluation. All right.
Ashay didn't send himself over.
Huh.
We practiced yesterday. He'll find the button.
Yeah.
All right.
All right.
Okay, so maybe I'll start asking a question. So Caleb, can you go to the slide where you have the Ellingham diagram?
Yes. Okay.
Yeah, so towards the end, you started talking about the silicon carbide and the silicon and potential disadvantage because of the reactivity, and that's shown here nicely. What other material now would you be able to use, looking at this diagram, that will give you the stability against carbonation or the formation of a carbide?
Okay. So this diagram is just showing oxides. And so if we use, basically what the result of this Ellingham diagram says is we can't use any oxides in the hot zone. Can't use oxide insulation, either thermal or electrical. But if I had an Ellingham diagram for carbides, basically what it would show, the reason I'm suggesting tin as an alternative material is because it doesn't form a carbide. And so basically if you have carbon and tin as your only elements in the system, there's no reaction that forms between them, and the solubility is just far lower, which is mainly because a carbide doesn't form. If a carbide formed and then dissociated at, say, like 2800 Celsius, like silicon carbide, that would increase the solubility. So because there's no reaction, the point of a change between carbon and silicon would be the failure of carbon itself, which is by sublimation at 3,000 something, 4,000, quite hot, high 3,000s. So that's why tin is much better. There's not really any other metal or cheap material that you can use. So like one alternative we considered for a while was maybe pumping a liquid oxide like alumina or silica, because these are cheap materials. But the problem is they have oxygen, and the carbon will pull the oxygen out and become a gas, and the wall will disappear.
Again, looking at the same diagram, since we are on the same slide, have you thought about cooling the pump?
So I don't think you could actively cool the pump because the liquid has to come out of the pump hot. But in some configurations, especially like, let me show the new configuration. The pump could be located in the cold spot. So like in this system, it's not, but if the pump reverse direction, it could always be in the cold section, which is maybe 1500 Celsius. But the problem isn't actually fundamentally with the pump. The pump could be made isothermal. In a large system, like in the full-scale TEG system, one second. When the pump is located in the middle of this tank, there's several meters of silicon around it. The thermal profile is really developed. So like there would be maybe less than 1 Kelvin temperature difference throughout the pump. And so you wouldn't really get dissolution at the large scale. It's just because these experiments are smaller that we observe it in the pump. The real problem is where you intentionally have heat exchange, so like the heater and the heat engine. And so there's some tricks you could try to play in those regions to prevent mass loss, like reducing the mass transfer coefficient by making the pipes bigger. There's a lot of things like that we looked into, but we're just so far from it working with silicon that it's definitely not practical. They could be useful for preserving the life of a 10 carbon system though.
And so remind me again, why do you need to put the pump in the hot section?
So in this configuration, the pump is a sump pump, which means it's inside of the tank. So the only way to get fluid out of either tank is by pushing it. And so then in this case, there's a pump in both tanks. In an alternative system where you don't have a sump pump, 1 second. In this system where the pump, first of all, there's no tank because it's a solid storage medium. So you see during charging, the pump is in the cold section, but this pump could also remain in the cold section during discharging if you reverse the direction of fluid flow. So like there's a lot of technologies now. For example, I think concentrated solar, I think their pump is only, at least the large pumps are in the cold tank. They pump cold salt up a tower and then it falls back down. So like there are ways to keep the pump
so I mean,
cold.
I was exactly thinking about that, using gravity. Which means that maybe one tank will have to be above the other tank. And you put in the cold tank in the bottom and pump from the cold tank.
Yeah, that's another thing. Like you could actually have one of the tanks physically higher on a hill or something. But again, the problem isn't really the pump, it's the heat transfer. So like the heater, for example, in this system, the walls of the heater would be gone in a day. And I don't think there's a way to resolve that just from mechanical engineering alone because heat transfer and mass transfer are coupled. Like if you make the walls really thick, it will last longer, but you won't get any heat transfer.
So you really think that the assessment of the technology is really a material problem. Is that right?
Yeah, I mean, I think the reason this initial version can't work is a material problem. I think, and we kind of probably expected that from the beginning, but we addressed and designed, all the mechanical systems to accommodate the only affordable material combination. And the mechanical systems finally worked. The pump rotated, it mechanically worked. It didn't melt or anything, but just the material limitations, I think, prevent pretty much any liquid from being stored and transferred at this temperature.
Well, but that's pretty discouraging because that's more difficult to solve. Oop, I lost connection.
Yeah, I can hear you.
Oh, okay.
Yeah.
I couldn't see my screen. And so it would be difficult to get away out of that.
Yeah, it's true. So, I mean, so the recommendation here is to change the material.
Yeah.
And if you change to 10, as you were saying, the price will go up significantly. Are you going to need the same amount of material? No, you're not, because you're going to just use a tin to circulate the heat, right?
Exactly. Yeah. So some of my lab mates are actually designing this now and running economics on it, but it's going to be cheaper actually. The performance isn't quite as good because now your storage medium is not isothermal and it's a little harder to get heat in and out of it, but the storage medium is cheaper and the volume of tin you need is quite small. Like tin is an order of magnitude more expensive, but you need at least 100 times less. So the cost of the tin is fine for heat transfer.
And what is the advantage of the graphite now here? Obviously, it will stand the high temperature, but any other advantage? Is it thermal conductivity or something?
Yeah, I mean, graphite's pretty excellent. Like it's the only material that doesn't have degraded strength with temperature up to 2600 Celsius. Its yield strength, like its tensile strength, remains, it actually increases slightly. So any other materials, like another candidate when you're using tin is tungsten. It doesn't react, but tungsten actually becomes quite soft above 2000 Celsius. So you could use it in some locations if it's needed, but graphite, you know, it's high thermal conductivity, low cost, and high strength. So I think it's an ideal material both for the pipes and for this thermal storage itself.
I mean, people have been studying fire brick heat storage.
Yeah, yeah. So that's a great material too. The difference is if you're going to use fire bricks, you're going to be 1000 Celsius colder because fire bricks melt at 1700 Celsius or something, which is fine depending on what type of heat engine you want to use. But if you want to enable the PV heat engine to get high efficiency and high flux to make it affordable, I mean that's the real driver to be above 2000 C is to enable the PV, a high performance PV heat engine.
So Caleb, back to the, you talked about these challenges in the previous section on the non-isothermal effects, and there's this delamination with thermal cycling. Certainly there are kind of many challenges. I know this is obviously a very non-trivial problem. You made a lot of great progress. Just curious if you have any recommendations for these. You kind of identified these problems, but where would you go from it other than obviously also moving to other systems designs, but where would be the next steps?
Okay. So like this slide, which is related to thermal cycling issues, is probably addressable. And this is actually an interesting slide because it's relevant to a related technology that several people are still working on, like Alejandro Dadas, which is latent storage with silicon at 1400 Celsius. So they intentionally have thermal cycling every day, phase change actually, which is even worse. And so they may experience this issue. So the problem shown here is in a way inconclusive because this experiment was run very quickly. So it's not obvious that you would get delamination if you thermal cycled more slowly. So there's a potential solution to this problem, but the non-isothermal circulation problem is really fundamental. And basically it's predicted by the phase diagram. Just the difference in solubility between the temperatures is 5 and 1%. And we were just hoping that the silicon carbide had some effect that reduced the speed of it. But in fact, it doesn't, which I've shown in at least 2 experiments, the pump and this separate experiment that I just did in June. And so really, I don't think there's a way to mitigate it with these materials.
All right, if no other questions, Caleb, I'm gonna attempt to move you to a second breakout room called breakout room 2. Just hit join, and then we finish our discussion. I'll close all the rooms, and I believe we'll all end up back in the main room again. There's still about 10 people hanging out.
Cool, okay.
All right. All right, I believe we have everybody back, so I'm happy to announce. Congratulations, Caleb, you passed. Dr. Ami. So I'll give him a round of applause in place, I guess.
Thank you.
And so you have done it.
Awesome.
All right. I wish we could get together and do our usual pizza celebration, something to celebrate you. Let's postpone it, and I guess we'll find time when the pandemic has died down to celebrate. But thank you very much. You've been a great student. Enjoyed working with you, and congrats on passing your defense.
Thanks. Yeah, it's been great working with you, and thanks to the committee for all your help, and thanks for everyone for joining.
Yeah, congratulations, Caleb. Very nice.
Nice job, Caleb. Congratulations.
Excellent. Congratulations.
We should have virtual champagne, huh?
Yeah, yeah. Yeah. All right.
So tell us about where you're going.
Okay, so I'm starting a job at DOE and the SETO, Solar Energy Technology Office, working on CSP under Avi Schultz. So I'll be reviewing some of Ashay's projects. No, by the time I get there, they'll be about over this version of the Gen 3 CSP. But I technically have no authority in this position.
Hopefully that will change in a short time.
Yeah, I think a lot of the fellows become technology managers in a year or two. So.
Well, don't hesitate to also move around DOE.
Yeah.
Once you become well known as someone that's technologically savvy in one place, you may get pulled to do other things and take hopefully some leadership positions. And I'm very happy that you've chosen to go there. I think we need more people like you in the DOE. So I'm excited to see what comes of it.
Yeah, thanks.
All right, I've got to actually jump off, but I will allow, everyone else can stay. I got a phone call I got to make. And again, congratulations, Caleb. And thank you all for coming.
Yeah, thank you.
Thanks, Ashay.
Congratulations.
Thanks.